Hi, good morning everybody. How are you doing? So my name is David Mulla. I'm the moderator for today's session. And I'm at the University of Minnesota in the Department of Soil, Water, and Climate. I do have a couple of announcements about today's program. Unfortunately, the first two speakers have canceled. So I'm going to be substituting for the first two speakers, and I'll be talking about a couple of different topics. One is irrigation related, dealing with a new institute that we're developing called the Artificial Intelligence Institute for Climate-Land Interactions. And then secondly, I'll be talking about spatial variability of phosphorus. And then we'll resume with the normal program. The other speakers are here. So I apologize for the disruption. But let me just start by saying that there's a couple of flyers in the back about our institute. It's AI Climate. It's a national AI research institute on climate-land interactions for mitigation, adaptation, trade-offs, and economy. Shashi Shekhar is our director. He's in computer science. And I'm a deputy director, Department of Soil, Water, and Climate. And so here's what our institute does. We work on artificial intelligence, cutting edge, new advancements like deep neural nets and other knowledge-guided machine learning processes to spur innovation in use-inspired case studies. Irrigation is one of our main focus areas. We're all aware that there's changing, patterns of our climate. We're getting more intense climate extremes, more frequent rainfall. Just a couple of days ago, we had these massive storms rolling through Starkville, and I think we're all awake at night listening to the thunderclaps, the heavy rain. Land is the second part. We're looking at interactions between climate and land, and not only in agriculture but also forestry. Those are big land uses in the United States. We're looking at the interaction, how climate affects farms and forests, and how farms and forests affect climate. And we're interested in mitigation and adaptation, which means reducing and absorbing carbon dioxide and reducing the emissions of greenhouse gases, enhancing resilience, and looking for trade-offs between the decisions that people have to make surrounding agriculture and forestry. Should I increase my production? Should I optimize my irrigation? Should I plant cover crops? Should I go to a completely different crop rotation? These are all trade-offs that have economic implications, and so we're looking at those kinds of trade-offs. So our vision is to transform the science of AI and decision support tools for climate-smart practices, and to create new tools that solve problems that haven't been solved before. We communicate with users and integrate their needs into our approach. The structure of our institute is built on research, education, workforce development, collaboration, and knowledge sharing, and then management and integration. And what we've heard from stakeholders is they are looking for models and tools that can help them evaluate the trade-offs and make their farming and their forestry practices more sustainable. To do that, they need data, and data is one thing that we really focus on. We're developing benchmark data sets for the United States and the whole world that can be used to train and test AI models. We're also involved in developing educational modules to help people in graduate and undergraduate education and the professional realms better understand how AI works, what it can do, what it can't do, and to become competent in terms of using and applying and developing new AI tools. So we have these strong internal partnerships and team building. We integrate research, education, and extension. We are the lead institution at the University of Minnesota, but we partner with Colorado State University, Cornell University, North Carolina State University, Purdue University, Delaware State University, and Prairie View A&M University. So we've got some deep networks that exist. Our research strategy is to use a co-design process where we conduct cutting-edge, use-inspired, and foundational AI research. We use a virtuous cycle to go between the domain science and the computer science. Here's the real details of everything we're doing in our institute. The left-hand column is our use cases. So these are practical issues that we need to solve, like better models for estimating greenhouse gas emissions, soil organic carbon, carbon dioxide removal, addressing climate risks, adaptation, and shifts in cropland forest transitions, and looking at, in particular, irrigation, multi-criteria, multi-objective decision-making to evaluate trade-offs, earth economy modeling so that we can put economy and ecosystem services on the same page and do that at the scale of the whole world. And in multi-scale, multi-criteria decision support tools, digital twins and things of that nature for soil moisture, for example. We just published a AI paper in the Computer and AI Institute conference, which is being held in Santa Clara next month. And it's on estimation of soil moisture content for the entire U.S. It's a very novel approach that combines AI tools like knowledge-guided machine learning with benchmark data sets from actual measurement sites at thousands of locations across the U.S. And we incorporate climatic data and remote sensing data from satellites to do the modeling. Some of the knowledge gaps that exist are out-of-sample predictions because of the variability and the sparse data that exists in agriculture. Hard constraints need to be included in AI models because the models can't just be used as black box tools where you don't have any explainability. So we're using mass and energy balance equations to constrain our models. We're involved in computer vision, perception, and analysis to actually identify objects and train our remote sensing models based on ground truth data from UAVs or cameras. Then multi-objective, multi-decision, multi-criteria decision making, which involves a trade-off between economics and ecosystem services. On the computer science side, the last column deals with the sort of foundational AI that we're using in our institute. We're using knowledge-guided machine learning. We're using combining learning and AI reasoning to do better optimization. We're involved in computer vision guided perception analysis with tools like YOLO and Segment Anything, and other tools as well beyond that, few shots and one shots. We're doing multi-criteria, multi-objective decision making with advanced AI tools, and then we're developing digital twins, for example, of soil moisture to help us develop more resilient systems. One of our sub-areas is climate risks and adaptation. And we have 5 focus areas here. So the one that this crowd might be most interested in is the crop hydroclimatic risks. So we're trying to predict future crop yields under climate change by looking at the interactions of CO2, soil moisture, and temperature, and also simulating what might happen in terms of need for future irrigation across the U.S. to basically adapt our agricultural systems in the face of warming temperatures and changing climatic patterns. So I think that's something that maybe a lot of you would be very interested in. To summarize, we face a lot of challenges in agriculture and forestry related to the extreme climate and the events that are changing every day. Land stewards need better guidance on adapting practices in ag and forestry. Where should they put regenerative ag or climate smart practices? Where should they use them? Which ones should they use? How long should they be used? And then, how can we help make those decisions and evaluate those trade-offs using AI by improving our benchmark data sets for training support tools, for developing more accurate predictions, and for scaling our algorithms, from the farms to the regions and from the regions to the farms. So we have to go both ways, upscaling and downscaling in a lot of the work that we're doing. I think this is going to benefit AI in the long run because we're learning, how to incorporate things like mass balance into the AI tools that exist. We're cutting, some new ground in terms of AI tools, and that includes multi-criteria, multi-objective decision-making and trade-offs. So that's the summary of what we're doing in AI climate. There are some handouts on the back seats, which you can take. They're free. And to read more about our, go ahead. Just if anybody needs them, they're on the back row there. So I'll stop here and see if there's any questions. Thank you very much. Yes.
Hi, Ezekiel Permans, from Virginia, working for the DoD, but here as an independent researcher. My question, as I see AI climate, very, very important part of the discussion, and throughout this whole conference we've been hearing about setting those standards. My question to you would be, where do you see AI climate's participation at the table in helping us see where artificial intelligence standards and AI climate interact and what standards would be set?
All right, so the question was about AI tools and then the standards that are being developed along with those. And you, by standards, you mean like ISO standards? Or?
ISO, or just what you see from AI climate's perspective
Right.
of what's important.
Right. So I know Alex, who's here in the room, knows a lot more about ISO than I do, and he's just issued a major report, which was rolled out yesterday from CAST, where they do a lot of discussion about ISO standards and the need to, have uniform protocols for data collection and management and interfacing different kinds of farm equipment products with other farm products. And I think that's an important area for further advances. If Alex wants to say a few more words about that, really, I think he's more of an expert in that than I am.
Yeah, not a whole lot more to add, I guess. I think there were two standards issues that were covered in the CAST paper. And one of those is around data standards, so that AI is more usable, if you will, for the data that are being collected in agriculture. And I see a group like Ag Gateway as being really central to that effort. Ag Gateway, if you're not familiar with them, are trying to develop data standards, data collection, data format, metadata, all of those kinds of standards for the use of agricultural data, not only in farming, but across the agricultural supply chain. Also, there are ISO standards and other standards organizations like ANSI, IEC, ASAE, who are beginning to look at standards for artificial intelligence. And I think this relates to so-called trustworthy AI or explainable AI, or the functionality. How can, if we're using an AI system, for example, in an autonomous machine, how can we be certain that this AI will perform its function as expected and not cause harm or just failed. So those are, hopefully that helps answer that question.
Thank you.
Thank you, thank you. And I think the issue of benchmark data sets is also really important here. There have to be really standardized protocols for collecting data. AI needs rigorous ground truth data in order to train and test models. Not every data set exists, not every data set can be actually used to train and test AI models. There's some data sets that really just don't have what it takes to do the right kind of training and testing. Any other comments or questions? All right, I think we'll move on to the second talk here today. And as I mentioned to you, unfortunately, the first two speakers did not show up for this session. So I was asked to step in and provide some information that could be possibly of interest to you. So the second talk for this morning's session is not about mapping, the economics. I think it was an economics talk. Actually, I'm going to talk about machine learning, modeling, and mapping of soil available phosphorus. So in precision agriculture, we need to enhance the profitability and the sustainability of our systems. Detailed information about soil fertility can be used to delineate management zones where phosphorus is the limiting factor. And what we want to do is avoid under and over fertilization, because that over fertilization pollutes the environment. Under fertilization reduces crop yield. So what we did in this project was we tried a number of different machine learning models. We used ordinary kriging, which was an older technology developed for predicting information at unsampled locations using semivarograms and linear weighted sums of observed values. This particular method does not use auxiliary variables like remote sensing. Generally, it's based on soil sampling. We use support vector machines, where we're trying to use either regression or classification to identify, information at unsampled locations. Bayesian additive regression trees is the third method that we use, which is a more sort of probabilistic method that uses the posterior probability of soil phosphorus to make predictions. And both SVM and Bayesian additive regression trees can use auxiliary data like satellite imagery or proximal sensor information. So the objectives were to assess spatial variability at a regional scale using a fusion of different sources of geospatial information with machine learning algorithms for commercial farm fields in Ontario, Canada. So we wanted to compare the performance of the BART, the support vector machine, and the ordinary kriging methods. We wanted to apply the trained and calibrated models to predict soil P at a 3-meter spatial resolution using the most highly correlated covariates we could find. We wanted to compare the accuracy of the machine learning techniques with the geostatistical approach, and then derive recommendations for where farmers should spread phosphorus and how much rate of phosphorus should be applied. And then finally to evaluate the economic implications. So the area we studied is in Ontario, Canada. We've got an eastern and a western zone. The eastern zone has 4 fields and the western zone has 3 fields. The yellow dots on this figure show the locations where we collected phosphorus samples by manual labor at about 2 samples per hectare. So it's pretty intensive soil sampling. But then we also brought in auxiliary variables from remote sensing and proximal sensing to complement the soil sampling data. And we fused the two sources of information to do spatial predictive modeling with machine learning and geostatistics, and then we got our outputs. So the flow of the work is shown here. It's kind of detailed. We had topographic attributes from 3-meter digital elevation models. We had proximal soil sensing of electrical conductivity. We had PlanetScope satellite data at 3-meter resolution. Then we had our measured data at 2 samples per hectare. And so we fused those data, and we went through a process for training and testing our models against the different scales, the in-field scales, the regional scales, and then the sort of global scales. Then we evaluated the accuracy. So here are some examples of some of the auxiliary data that we use. There are actually 42 different variables. I'm just showing you 8 of them. Elevation was collected at 3,000 samples per hectare. This chlorophyll green index from Planet was 3-meter pixels. The ECA or HCPE1 was 0 to 1.6 meters, 2,885 points per hectare. At a deeper depth, we had the same information for the same density. We had red and NDVI in the green, which were then obtained from Planet. And in our ground truth data were the soil samples for pH and phosphorus, which were 2 samples per hectare. So the descriptive statistics of our phosphorus, the mean was 16 parts per million in the eastern zone and 24 parts per million in the western zone. According to the Ontario Department of Agriculture, any soils that have less than about 31 parts per million of phosphorus should respond to phosphorus fertilizer. So on average, you would say, okay, let's fertilize all these fields with phosphorus based on this average value. Well, as I'll show you, that's not a really wise decision because there's a lot of spatial variability. So let me get to the technical details of the BART model. A BART model started out with all 42 variables, and then we eliminated the ones that were least important. We arrived at 6 factors in eastern Ontario. Those are the ones shown on the upper bar graph, and 4 factors for western Ontario. And you can see the names of those variables. Elevation was the most important predictor for both zones, and then we had some infrared, some satellite imagery data that was important at both sites, and ECA data was more important in the eastern zone. So the variables differ somewhat from each region, but elevation and remote sensing are very important. We look at the performance of our machine learning models. You can see that the BART had the lowest RMSEs compared to the support vector machine, and the highest R-squared values. So it performs better. It doesn't need as many auxiliary variables in order to do the prediction. With the SVM, we found that it liked to bring in a lot of auxiliary variables, like 15 variables for the eastern zone and 12 variables for the western zone. That's a lot of auxiliary variables. We then said, okay, what if we just took the variables that the BART model said were most important and trained the SVM model with that, and that's what the SVM6 star is for the eastern zone, and that still didn't perform as well as the BART model. So BART model was the best performing model. Here are some examples of spatial predictions for available phosphorus using SVM on the left, BART in the middle, and then the ordinary Kriging on the right, which doesn't use any auxiliary variables. So you can see right away, using those auxiliary variables like remote sensing and electrical conductivity helps a lot to give us better predictions of spatial variability. And the patterns really look very different if you don't use auxiliary variables. We also can calculate uncertainty with these models. So here are uncertainty maps with SVM on the left, BART in the middle, and ordinary Kriging on the right. And from the scale, you can see that the uncertainty of predictions is lowest with the BART method. We're down at, 2 parts per million or 3 parts per million, whereas with ordinary Kriging, we could be as much as 25 parts per million for our uncertainty, which is huge. All right, so then next step was to actually do the mapping and decide on what strategy for management should actually work out. And so and we had 2 different findings. One was there's a set of fields where variable rate nitrogen was really the best option. And there was another set of fields where uniform application of nitrogen at low rates was the best option. So the top row here shows an example for the field KN, which required a variable rate application strategy. So you had some areas getting 20 kilograms of phosphate, some 50 and some 70, which is the conventional rate that the farmers are using, 70. On the bottom, you see another set of fields where we're recommending a uniform rate, and in this case, it happens to be about 20 kilograms. So it's a very low rate compared to the conventional rate of 70. Now, here are all 5 fields that require that uniform low rate. There are 5 fields here. And on average, we're saving 50 kilograms per hectare of nitrogen for all 5 of these fields by using our methodology. That's a huge savings. Here are the 2 fields where we recommended a variable rate strategy. So spatially varying the rate of fertilizer from 0 all the way up to 70 kilograms per hectare. And the LN field requires very little, variable rate nitrogen fertilizer. It's only about 20 kilograms, and the rest requires no fertilizer whatsoever. So there's great savings on that field, the one on the left. The other field has a higher requirement. There's a large area that requires about 50 kilograms of phosphorus per hectare, and the other quarter requires about 20. So these have cost implications, and reducing the P rates using our approach resulted in a profit of about 15 to 16, all the way up to $72 per hectare, including the cost of doing the variable rate application and collecting the data. So this is really a big factor for farmers that, they can make a lot of money by changing to these practices. The greatest profit occurred in the uniformly fertilized fields at a low rate, which saved 50 kilograms per hectare of phosphorus. And then you had more moderate, profits in the other 2 fields where we were recommending variable rate. So our conclusions here, there's big economic savings from doing this. The BART method is the most accurate of the 3 methods we tested. And this work has been published. You can see the first a reference here if you're having any questions. Thank you very much. If you have any questions, I'm happy to answer those.
Yes, good one. I probably have 2 questions. So number 1 is, for ordinary Kriging, you can use a co-Kriging process by bringing auxiliary variables to boost up your performance, model performance. So I wonder if you can apply those variables that you selected from BAR, and then use a co-Kriging approach to maybe to improve your model.
Yes, yeah, that's a really good suggestion. We didn't try that, but we thought about it. It's just that we ran out of time for doing all these different models. But I think that would be another approach that could be very helpful in terms of improving predictions.
Yeah. So the other one is I didn't follow is when you do a variable selection, what's your criteria for you to decide, okay, these are the good variables we need to move on?
Yeah, the criteria are kind of complicated. Let's see if I can go down here to the bottom and show you another slide on that. I don't know how this works. Trying to advance. Anyway, basically what we're doing in our criteria is trying to optimize the model by reducing the RMSE. And so we're looking at the variable influence that different parameters have on each other and their cross-correlation, and removing parameters that are highly cross-correlated to get to the ones that are most important. All right, so now we're going to move back into the normal program, and our first normal presenter, sorry, I was substituting for some others, is Xiyu Liu from the University of Florida. And let me close this and open your presentation.
Okay, so hi everyone. Okay, hi everyone. My name is Xiyu Liu, and I'm a PhD student from University of Florida. And my supervisor is Dr. Yanis Amtidis. And today my topic is our lab's latest product is our AI-driven precision square with a canopy-specific parameters optimization for the enhanced field efficiency. Okay, so here's the introduction. It's like why we are making this smart sprayer. And so our target is to develop AI-enabled smart spraying systems. And we aim to optimize the pesticide and nutrition applications in the field. And also, we want to achieve our goals mainly by automatically adjust spray speed, the flow rate, and the coverage area based on the real-time measurements of our tree canopy, density, and the height. And so this is very important because it can reduce the off-target spraying, and also it can help us to reduce our pesticide loss, and also help us to improve the spraying efficiency and enhance, is very good for our environment. Okay, so let me introduce our key components and the whole architecture. So first, we use the dash camera, which is from the Intel RealSense, to capture the images of the field. And then we have this field canopy data. We use these videos and input as an input to our NVIDIA Jetson Xperia, which is already built with the AgriSense AI, which I introduced yesterday from our poster. And I will briefly introduce the AgriSense. This is a system that can automatically analyze the tree canopy density, the tree height, and it can count the tree numbers and finally do the fruit count. So after this, we can get our tree canopy density and height estimation. We use this and send some commands to our microprocessor ESP32, and which is a free real-time operating system, and we use this as a slave controller. And then it sends demands to our DC motor valve, and which can help us to control the liquid flow, and we send commands to the nozzles so it can spray. And also we have this hexagonal dumper, and which can use to adjust the fan inlet size. like to control the air input. Okay, then it's like an overview of how our sprayer really looks like. So you can see at the front we have this RGB depth cameras at the front to capture the images. And below we have our control box, which has all of our microprocessor and all the other like GPU, GPS, IMU inside. We make it into a control box. And also we have each side we have power box, which can supply as like battery supply for our processor and our cameras. And finally, at last, we have these nozzle cables which connect to our nozzles. And also at the back of our tractor, we have this remote control dumper, which can control the air input and output. Okay, so come to our experiments. So we divide it into two parts. So the first one is the pre-test. So we test it in a test field to like try to figure out what's the nozzle sprayer range, so it can cover what the tree canopy. And also we evaluate the coverage across the canopy zones. It's like you can see here we have several zones, and we test how our nozzles really works. And also here is like in the field it's like a framework like that. So you can see our tractor move in the middle of the tree rows, and it can spray for both two sides. And the second part is our field test. We test mainly on three canopy density levels. We have this small, medium, and high. And also we test like 5 citrus trees per level. And also how to measure, we use the water sensitive paper at the front, middle, and the back of each canopy, so we can see how the sprayer really works. And also we verify the fanning light size and the valve settings, so we want to figure out what's the best for the sprayer to get its best efficiency. Okay, finally comes to the result. It's like during our experiments, we find out it's like 28% increase compared with the regular sprayer. And also it can efficiently reduce the spray drift, and also it can reduce the off-target spray loss. And also because we also have the GPS and IMU, so we can automatically adjust our parameters to make it work very smoothly. So, and also for our system, I think the best thing is quite eco-friendly, because like you only spray where you want to spray, like the tree trunk, and you don't want to spray it into the weeds. Like when you're doing the nutrition, you don't want to give extra to the weeds. You really want to give it to the trees. And also it's quite good for the farm management, because like for this, it can help you to more customize like which tree you want to spray specific fertilizer or pesticide. You can customize it. Okay, and here is our user interface displayer. It's like from here you can see like the longitude and latitude, like the location of your tractor, so you can know where it's actually moving. And also you have you can control the GPS, the cameras, and so you can know everything about how your tractor is working. And there is also like the zones, the settings, so we can know like which area of your field is actually being sprayed. So, and also on the right side is like the settings of the user's interface with the control inputs for our spraying system. So you can, here is like, you can set up the distance between the sensors and the valves, and also you can set up the spray buffer, because it's approximated area where you want to spray. And also here is like, you can apply it for a specific tree or you can apply it for all trees in the field, so it's totally cosmetic. So yeah, it's quite, another thing is quite easy for end users to use, and it's like you are a technical specialist or you are just a farmer, so it's quite easy and to understand and to operate. Okay, yeah, finally I want to introduce our result. It's like you can see from here is a heat map of our spraying in our citrus field. And you can see that we generate our heat map, and you can see like exactly how many volume you spray for each tree. And also there presents some speed of your tractors and the flow and the total gallons. And also because our AgriSense also have the fruit count, there is also fruit numbers showing here. So yeah, I think that's also any questions or comments.
When you were coding the UI, did y'all look at what language y'all were going to use, and how did you go about developing the UX for the system?
Actually, it's like the basic website development, like Java, and also for the Outlook, we use the JavaScript, like to develop everything. And it actually linked to a database contain all the information that we know about the field. It's like everything will store in a database first, and we present it as a software or interface to our users. Anything else? No? Okay, I think.
But we have more time. There's
Yeah.
still a couple minutes, so.
When you were looking at the engineering side of this, and you were building the sensors, did y'all look at what type of sensors you wanted to use? Because I saw you use LiDAR and then computer vision.
Yeah. Yes, but everything really comes from the depth camera. It's like it will come up with the RGB image and also the depth image. And our software really comes from the AgriSense. And so, and it's based on like machine learning stuff. So we use these pairs of RGB and depth images as inputs to our machine learning models and come out with the result. And also for the LiDARs, if you want to more precise result, or maybe you want a cloud map like that, so you can use the LiDARs here. And I think the result is quite good, quite precise.
Thank you.
I'm curious about the marketability of this. Do you have intention to take this to market in some way?
Yes. Yeah, we want to make it like commercial. And maybe we're thinking about we can sell our product, because everything we can make it portable. But for the end part, the down term, we can help send some technical specialists to the farmers, and we can build everything for them. And we can do the test drive maybe and see the result, help them to learn how to use it. Yes.
All right, thank you very much.
Thank you.
All right, so our next speaker is Gigi Chen from Florida A&M University, and she's going to talk about growing precision engineering systems for grapes. Okay, thank you very much. And I'll give you a warning, Mr.
Okay, that sounds good. All right, good morning, everyone. How are you doing?
Good morning.
Good, good. So my name is Xin-Chu Chen. I am an assistant professor with biological systems engineering in the College of Agriculture and Food Sciences at Florida Agricultural and Mechanical University. And today it is great to have this opportunity to talk to you about this exciting work, which is growing precision engineering system for muscadine grape vineyards to aid climate smart agriculture. So let me start with a little bit of background and motivation. So muscadine grape, they are native to the southeast US, and they thrive in the humid and warm environments where other varieties of grape typically struggle. But water management is very crucial for muscadine vineyards as well for several reasons, including irrigation needs, disease prevention, soil health, water use optimization, and fruit quality improvements. So to monitor the soil, the vine, and the environmental conditions are essential for efficient resources use and vineyard management. And then let me introduce you a little bit background about our resources. So Florida A&M University is a HBCU, and we are the #1 public HBCU, and we have this umbrella under College of Agriculture and Food Sciences. We have Center for Viticulture and Small Fruit Research, and this center is recognized internationally for the warm climate grape research, and the center maintains the most extensive muscadine grape germplasma collection in the world, and this is one of the 5 national clean plant centers for grape. So we do have a great resource. But looking at some of the gaps here, we are lacking of some information regarding muscadine irrigation. So when we concept the project, we want to build this precision engineering system that can do some of the near real-time monitoring in the vineyard to provide some of the decision-making information regarding water management and disease management. So we piloted this project using 9 muscadine grapevines with 3 wine varieties, 2 red wine variety, including Noble and Floriana, 1 white wine variety, A27. So we want to deploy the Internet of Things sensors and network communication, and then we want to build the precision engineering system. And we also want to facilitate the student experiential learning on precision ag and digital technologies, because we are academic programs and we do education. For me as an assistant professor, I have a relatively high teaching load. And we also want to increase the community engagement through extension and outreach. So let me show you a little bit of foundation of this work. We finished a AG2PI seed grant in 2022 that based on that outcome, we were able to build an online portal here within the Peer Learning Agriculture Network, the plan. This is an in-house developed website, and it can capture the different data types from the data generated in the farm, for example, like when to spray, when to harvest, when to apply some fertilizer, and how else we can take some images and then store it in this portal. And this is like a user secure. We can create an account for each for farm manager, each user, like a student or researchers. And then the portal also can gather data that is monitored by the IoT telemetry sensors. And this is, here, this is a 55 acres of research vineyard located in the east side of Tallahassee, Florida. And it's, so we basically created this portal, this portal to store those information, and this is a customizable. We can create it based on the user's needs. For example, if we demonstrate the portal to farmers, to growers, and then these are some features we can introduce. And then through the project, last year we were able to deploy the Internet of the Sensors and Network We did this in February 2024, early growing season for muscadine grape. And we have installed 9 setups of canopy cameras and sensor arrays, including the soil moisture probe, rain gauges, relative humidity sensor, temperature sensor, and leaf wetness sensors, and also weather station. And this is our in-house designed, I'm not sure if I have pointed here, maybe it doesn't work for this screen, but the upper right corner, that is our in-house designed canopy cam with the edge computing node. Let me show you here in a minute. And then this is how it looks in the field. So above the canopy, we have the Raspberry Pi powered canopy cam above the canopy, and it's powered by the solar. We don't need any extra power in the field. And then this is our weather station. And underneath the ground, we have those different sensor arrays, like buried underneath the ground. So we implemented the edge computing sensor node. This is the camera that can capture and processing the canopy cover images on site and then transfer back to our server, which is that website I showed you earlier. And we developed the image analysis algorithms using Mahalanobis algorithm for automatic data collection and analysis that enabling the estimation of canopy cover and grape percentage that can show using the website. All right, so we use the portal for data aggregation and visualization, so the near real-time data can be accessed by researchers, students, and the growers. And we integrated the LoRaWAN technology for our low-range, low-power data transmission from the field sensor back to our central database. Also, the weather station data, also we can use the API to transfer back to our central database. And let me show you some of the results in the field. These are one of the demonstrations from one of 9 vines we monitored last season. The canopy node installed above that can capture the canopy images every 20 minutes from 7 a.m. to 7 p.m. Because of the power, we want to save some power from solar during the night. So we just program the canopy cam to sleep. Okay, you go sleep during night, and then 7 a.m. hey, wake up and then do your job. Take the images every 20 minutes. Okay, and then the raw images will be stored on site, and then the machine learning algorithm will process the images on site and then transfer back the canopy cover and grape percentage to the central network. So the LoRaWAN is the transmission protocol, which will work with narrow bandwidth with low, basically kilo-sized data. So instead of transfer back for megabytes image data, we also transfer the precise kilo-sized data. All right, and this is a example to show how it changes for that canopy cover alone, like during the season. This is captured for last season, April to June, and we do have like the whole season last season, and this year we start a new season. And here is an example for the near real-time soil volumetric water content that collected in one of the locations. We do 3 depths, 0 to 1 foot, 1 to 2 feet, and 2 to 3 feet. So we have the sensor every 4 inches, but we aggregated the data to show 3 depths. Because of the muscadine grape is a shallow root creature, so you can see the water use variation will like show in the topsoil, typically 0 to 15 centimeters. All right, and here the higher number indicates the wetter soil and lower number indicates the drier soil. And this is another example for the near real-time soil temperature that collected using one of the location, and same 3 depths, 0 to 1 foot, 1 to 2 feet, 2 to 3 feet. And again, the topsoil shows the greatest variation for the soil temperature. And here is a demonstration of the near real-time ambient relative humidity and temperature that collected for our wide wine variety, Floriana. And this is the near real-time precipitation and leaf wetness from last season. And the weather station helps us to manage and monitor 12 parameters for the ambient environment. So under near the vine, we have the metals station. So if we have some, for example, missing data or some of the growth of the vine during the season, the leaves kind of like cover those metals station. We use the weather station kind of to help with those missing data. All right, so this year we just we installed our upgraded canopy cam in the early March. And this year, because the winter, we have a colder winter compared to last year, and you can see the bud break stage is late this year. So we initiated the feature for grapevine bud detection because the bud break images is very critical for muscadine grape. They need the water during that time. And for developing the bud detection feature, we use the deep learning algorithm ULO, and we use the images collected in the field last year as our training data set to train the model. And we have some of the validation data set separated from the training data set. And this year, we are going to collect more as a field ground truth to test the algorithm. All right, so through this project, we were able to initiate a digital ag and plant phenotyping technology experiential learning opportunity. We were able to provide a semester-based internship and also summer internship for our students, including graduate students, undergraduate students, and community college students. So through this, it provides a strong support for HBCU students and also add the digital ag components to our curriculum and also help with recruitment from a community college, and then they transfer to our university to finish their bachelor degree. Here's more pictures about they got a good learning opportunity, and we'll also use this this project, this platform to provide community engagement through extension outreach. Some of the platform including annual Florida A&M University Grape Harvest Festival. We typically get about like 2,000 participants, so we can showcase how does it look like for this project. We also engage with other community in, for example, Albany, Georgia, some international connection with Kenya Edgerton University faculty. They also get some training from us. So to summarize, during this past year, the first year of this project, we built the very first precision engineering system for near real-time monitoring for muscadine research vineyard. At Florida A&M, we want to take this as a test bed to show some of the advanced engineering technology and how to use them, especially for stakeholders, the growers, researchers, students, how they can use those data to do more analysis. And we were able to build the infrastructure and platform for students to use to learn digital ag and plant phenotyping technologies through the project. And one thing I want to mention about this environmental resilience, last year we do have a lot of challenges regarding the extreme events, okay? In Tallahassee, Florida, well, the 9 setups, they survived from several heavy thunderstorms in April and May, and we had one tornado in May 10th, and we have 2 hurricanes, Hurricane Debby and Hurricane Helene. So very fortunately, our setup, they survived. They're still functioning very well. And the system helped the farm manager to detect some of the deficiency of the irrigation emitters. So we were able to replace those things to help the farm management. All right, so with that concludes my presentation. I want to thank our funding agency, National Science Foundation, to provide us funding support students to do experiential learning regarding digital agriculture and plant phenotyping technologies. And also thank USD NIFA for all their support for research, extension, and education. All right, thank you.
I think we have time for only one question, sorry. Anybody have a question?
As a result of all the challenges of last year,
Uh-huh.
how was the harvest?
The harvest, so last year, because the latest season we have a very wet season. So you will see from our monitored canopy images, you will see a lot of disease. For example, the angular leaf spot and black rot developed later in the season. Even if we do regular spraying, but a lot of wash off because of precipitation. But regarding the harvest, it was compared to the year before, not that bad. We still be able to get averagely like 100, close to 100 to between 100 to 150 pounds per vine. And then we're using those vines to making wine. It's actually right now it's in fermentation stage.
Thank
Yes.
you. Thank you very much.
Thank you very much.
All right, we'll move on to the next speaker. Let me get it set up. All right, Samuel Ravindran, sorry. Is going to talk about Agro-LLM, retrieval augmented generation and large language models. I'll give you a warning this too.
Good morning, everyone. I'm Dinesh Jacques Samuel. I'm an assistant professor in Pittsburgh State University. So I have a background on computer science and engineering, and I used to work with computer vision and large language models recently. So today I'm going to present an agriculture specific LLM called Agro-LLM, which bridges the gap between the theoretical knowledge and the practical applicability for the farmers. So, large language models are transforming the agriculture in decision making, precision algorithm, and knowledge sharing. And Agro-LLM is the kind of one which helps to have a agriculture specific LLM which helps in decision making and knowledge sharing for the farmers as well as in education. So here in this LLM it's more specific about the agriculture information. So we train the model with we have the model with the agriculture related data set, which has the data from the textbooks which are referred in the universities. So this Agro-LLM can be used as in education as well as it can be used for decision making in farming. So, and LLMs are prone to hallucination, which means like they are asked with some specific questions in related to the core fields of agriculture, then the LLM may come up with some irrelevant responses. So to overcome this challenge, like we have used the RAG, which is the retrieval augmented generation, which helps in retrieving the information which is specific to the query, and it will generate the response with some more relevant answers to that query. So the Agro-LLM can be used in education because like we have used the data which are the textbooks which are referred in the universities, and it can be used as a teaching assistant as well as it can be used in the farming, used by the farmers for having some decision making regarding the crops. So here we use the structured database where we have taken the fields, 4 important fields from the agriculture, and then we have taken all the categories, all the subfields within the 4 important fields, and we have retrieved the textbooks and we have used those textbooks for as a database for this Agro LLM. So the methodology and overview. So here it's more of important thing is about the data and then the prompt engineering. So data and prompt engineering makes the LLM stand out compared to the other LLMs which we have in the agriculture field. So the first thing is we have categorized the data into 4 fields. So one is the life science. One is the life science, agriculture life sciences, and the agriculture management, agriculture forestry, and agriculture business. So within the agriculture life sciences, we have the subtopics like agriculture policy studies, agriculture law, agriculture communication, and emerging research fields. And within the agriculture management, we have the subtopics like agriculture business, finances, and then land and resource utilizations topics. And the third, we have the agriculture and forestry. Within the agriculture and forestry, we have topics like crop and soil sciences and horticulture. And we have agriculture business category. Within that, we have ecological restoration, dairy sciences, organic farming, and animal science. So these four are the 4 main topics, and within that we have the subtopics, and we have tried all the textbooks which are referred in the universities for all those subtopics, and we have used that as a data for this LLM. So the framework. The framework consists of a database, which is the so once we retrieve the text and the embeddings from the data which we have, and then we are storing that in a database, which uses the Facebook AI search, which is the FILES, which is a vector database, which is good in retrieving the information from the database. And then we have used a RAG, which is a retrieval augmented generation, to retrieve all those information which is stored in the database. And then we are giving that retrieved information plus the engineering prompt to the LLM, and then the LLM will be generating the response based on the retrieved information and the prompt. So we have come for evaluation. So we have compared with the LLMs like Gemini 1.5 Flash, ChatGPT 4 Go Mini, and then Mistral. So we have compared the model with 3 types of LLMs. And here is the workflow of it. So here we have the user query. We have the user query, which is given by the user. Once the user query comes in, we'll be extracting the embeddings from the user query, and then it will be passed to it, and we will be sending that user query to the vector database, which already has the embeddings from the database. And within the database, we'll be searching we'll be doing some similarity search, and we'll be searching the information which is related to the query. We'll be matching, it will match, and it will find all those information which is related to the query, and it will be retrieving those information. Those information will be passed to the LLMs along with some prompts. So here the prompt engineering plays a major role here, because if we are giving the right prompt, it will answer, the LLM will come up with some accurate answers. So we have used the prompt engineering, and the prompts plus the retrieved information is given to the LLMs, and the LLM will come up with a response from that. So we are just narrowing down the search for the LLM, and we are so that we can come up with some accurate answers rather than having some hallucination in generating the answers. So here is a view of a database which has the large amount of information, which are the chunks of information. So this is how the vector database will look like. So it has the embeddings which are from the database which we have. For example, here we have the information from the chunks, or the chunks of information from the textbooks. And once the query comes in, once the query embedding is passed to the vector database, it will search the information based on the query embedding, it will try to find all the relevant information from the chunks of information, and the RAG will retrieve, finally the RAG will retrieve all the relevant information which is regarding to that particular user query. And then the retrieved information is, along with the prompt, is passed to the LLM for generating the response. So here is the overall integration of the system. So here we have the user. The user will give the query, and the query will be extracting the embeddings from the query using the embedding models. And we have the database, which is specific to agriculture, and we have the documents, which has the textbooks, and we also have we included the research articles and few blogs which are from reliable sources. And then those from those documents we will be extracting the text, and then we will be giving that to the embedding models. The embedding models will convert those texts into embeddings, and those embeddings will be saved into the vector database, which has the Facebook AI similarity search for searching the content within the vector database. So now, when the user gives the query will be passed to the vector database, and we will be searching for the relevant information based on the query embeddings. And then the RAG comes into the picture, and we'll be retrieving the information. And then we are using the retrieved information along with the prompt and pass that to the LLM. And based on the information and prompts, the LLM will be coming up with an answer. And in case if the query, in case if you are not able to find the information within the vector database, then it's the query will be passed directly to the LLM, and the LLM will come up with some answers based on what it has, based on what it was trained on. So here are the model evaluations. So we have evaluated the model using the mean reciprocal rank, recursion, and blue score. So these are all the evaluation metrics we have used to evaluating the model. So we evaluated the model based on the relevancy of the response it was generating for the query. And we have categorized the data into the 4 main categories of agriculture. So agriculture, life sciences, management, agriculture, forestry, and business. And finally, we have also the precision algorithm. So we have used 120 questions from the precision algorithm textbook, and we have evaluated the model. Based on the response generated by the model for the 120 questions, we have come up with some accuracy scores and the time complexity. So here, in overall, the ChatGPT 4o mini performs well with an accuracy of 93%, and the average time for one query is around 10 seconds. So of course, it's going to be huge. But Gemini, in Gemini, like the performance is a bit low. It's around 84%, but the time complexity is good. It's better than the ChatGPT. So these are all the things which we come across after the evaluation. So key findings. So ChatGPT 4 mini with RAG provides a better performance for agriculture queries. And of course, we have used our files vector database for doing the similarity search for similarity search and retrieval of information. And RAG-based responses improves the response without hallucination. And conclusion, so it bridges the gap between the theoretical gap and the practical applicability for farmers, and also it can be used as a teaching assistant for agricultural studies, and it is more specific. It has a more specified database for agricultural information, and ChatGPT 4.0 performs better. And in future, like we plan to include the real-time IoT agriculture data so that it can come up with some data insights for the agriculture, and we can plan to include also the multilingual, multi-language support for global farming communities, and it also we also plan to enhance the skill for adaptation. Thank you.
David, you have the one question.
Okay, great. It's really good to see that RAG is giving some good results. Where the models fail, are they failing because RAG failed to pull out relevant information, or is it failing or something else?
So, if the questions in, if the query, user query is out of the context which we have in the database, then the model will fail. In that case, the query will be passed directly to the LLM, and the LLM will come up with some answers with its knowledge. Like if you are using the ChatGPT API chat, it will give the response same as what ChatGPT is giving us.
Thank you. That was really an interesting talk. I'm sure that we could have had a lot of questions on your talk. All right, Ezekiel, you're up next. I'll get your presentation loaded. So Ezekiel McReynolds is going to be our next speaker, talking about cybersecurity in AI-driven agriculture.
Good afternoon, or / good morning. We're kind of right in the middle of both. My name is Ezekiel McReynolds. I'm a data scientist that works at the Department of Defense. My background is I'm traditionally trained as an agricultural engineer and was given an opportunity to apply modeling and simulation through the techniques that I learned from biological simulations into the Department of Defense's questions when it came to modeling and sim. However, here I'm an independent researcher, so all of these statements and opinions that I make here are of my own. They are not of the government, and they are not of my current employer. So with that, I'm going to step into, that's probably the wrong button. There we go. Step into the next one. So cybersecurity, what is it, and why do we care? The analogy I like to give is you had a group of archaeologists and they plotted out 3 spots that they were going to dig down to figure out who was the most advanced technological group of our time. They dug down in New York and they found phone cables, and they said, wow, they were way ahead of their time. They were able to give a great representation of technology. Then they went out to California and they dug down there. This has fiber optics. There's no way there was anyone more advanced than here in California. And then they dug down to the same depth in West Texas and found nothing. And they said, you know what? Nope, West Texas, most advanced civilization ever, they had wireless. That's why I'm here. We are getting a connectivity that's bringing everyone closer. That's a great thing, but with connectivity does come a level of vulnerability that I want to bring an awareness to. The threat landscape of critical infrastructure is expanding and growing at an alarming rate. I'm going to get further into it on a ransomware topic, but it's a multi-billion-dollar industry from a hacker side and a cybersecurity side. So where does agriculture fit in such a large industry? And then the emerging technologies that we're here talking about today, that underpinning is data, connected data, and now we're adding in on top of that another convoluted layer that can be simplified into AI. So I have a couple of things up here to talk about. Windows XP has now officially overtaken Windows 8. And the question is, hey, why is that? It's solid, it runs, but it does have certain vulnerabilities. We're bringing technologies into areas where Windows 95 still may be running on certain aspects of equipment that we are introducing in Internet of Things. So as we move forward and bring this connectivity, we need to be mindful of what does that mean. Not that we need to get rid of it, not that we need to push it out of the way, but what does that mean? And as I mentioned here, in the critical infrastructure, we have had hospitals ransomware. We have had the Colonial Pipeline, our energy intake in the US, shut down for a certain period of time. we need to start thinking about, as we bring in those technologies, what are we going to do about it? So, IT, information technology, OT, operational technology. Precision agriculture is where we meet in the middle now. It's not IoT, that's Internet of Things, very important, but not here. So what I want to kind of set the playing field when I talk about this is the use of computers and software to store data, information technology. It's really trivializing it, but that's important to understand. Operational technology, supervisory control and data acquisition. We just talked a lot in the industry over there about what we're going to do with Isobus. So that's an operational technology that is getting connectivity and creating data, thus becoming an information technology in the process. So we need to understand that this is happening, and we are the drivers for the agricultural community, the vendors, the research institutions, the extension services. We need to help translate what that means. So here I am going to talk about the attack surface that is cybersecurity and what that is. So I went in order of severity. So least severe to the most severe. They're all severe, but what I see from my vantage point of what could happen as we move forward as a community bringing precision agriculture to the world. Data poisoning. It's a type of attack where you're able to get into the AI model and change and manipulate. This is a very high-level thought process. It takes a whole lot of manipulation and understanding of various things. In the cyber world, we kind of think in scales of threat actors, and this is something I would say, again, my opinion, a nation state would be looking at doing. Something from a very critical infrastructure, very silent, very unknown. Then we get into botnets. Now this is where the rest of the hacker community is going to kind of sit, because now we're setting up a whole bunch of open internet devices. So what is a botnet? Botnet can be a whole lot of things, but basically imagine it as one computer having a whole bunch of spiders, telling those spiders where they want them to go, and you can knock other things off the internet. So I see in the near term, we're going to have a lot of intrusions that don't do a whole lot of damage to the sector itself, but is going to utilize it as a vector into other sectors. That's where I see one of the very first applications in an IoT standpoint from sensors and other aspects. Now the most important one that I'm here to talk a little bit more about today, which is ransomware. I'm sure we have seen aspects of it in our daily life. It is a billion-dollar industry now. There is an entire industry set around developing an infiltration, selling that as a product, selling it to other people to then implement. And we know that if it's a critical infrastructure now, it is a place where they can make some money. And so as we think about this, again, I'm just stomping my foot over and over, we are creating great opportunity, but we are also creating a very unique space for actors that we haven't really been considering. Because I came from an agricultural engineering background, and I had no idea what happens when it means we enter the internet. So I've already talked a little bit about it more. I'm going to drive in a little bit more. AI, ML. A Ukrainian general came out and said, oil was the past. The most important resource we have as a society today is our data. We are becoming a data-reliant society. Now, it seems like in the back of your head, like, no, I know I could be on my own. And I can tell you, for my generation, backwards now, we lose our phone, we freak out. So there is a level of data reliance that is being created in the information age that we need to understand. And it's something that it's important because in order, as we saw at the very beginning, the population is going to continue to increase. We're pretty much set on how much land we can use to farm with. So precision agriculture is super important. I don't want to be up here and say, we should never go into it. That's not what I'm saying. I really want us to go there, but I want us to go there in a very systematic and safe approach, because if we do not secure our emerging technologies we don't set up those preparations for what we can do as researchers and bring awareness. Yes, not the cybersecurity awareness that you click through and you never look at, and then you click on a link and we're back to square one of looking at it. This is a discussion showing people what interconnectivity looks like. And so data is our most important aspect of our day-to-day lives as we move forward in this AI, ML industry. So, now my suggestions. They're going to seem simple, but it's kind of not forehead slapping obvious, but it's the same things we did when we were running DOS. You didn't trust your computer. You still shouldn't trust your computer. Backups, data. What happens when the implementation plan, and you need to set that forth. So we're going to talk about resilience over prevention. You're never going to build a strong enough castle, and that's okay. We're in an open source community, and we should be an open source community. So what does that look like for us as a community? Incident response and recovery plan. As a university and an extension service, I think it is our duty to start looking at the opportunities that we can start introducing. Not only we're saying, hey, here is a way to create data, here is a way for us to help you set up and secure your data. And lastly, because this is an AI conference, and I know I'm stomping on data and I'm stomping on all this other stuff, there's a very, very unique aspect to AI-driven threat detection when it comes to implementing a critical infrastructure. What I mean by that is there's a concept called a zero-day. A zero-day is a type of hack that no one in the community has ever seen before. We're trying to implement this now in various areas, but it is showing very effective because human interaction is the key to how we look at and find those new threats. So, with that, my conclusions is securing AI in agriculture is not just about protecting the data, it's about ensuring global food security. So at this time, I'm going to just open the field up for questions.
Thank you so much.
Thank you. Yes.
Do you currently see a need for risk assessments in the agriculture space? Because currently I'm part of a Mississippi State team that's doing cybersecurity assessments for K-12 schools and small businesses. We're looking at other areas of critical infrastructure. So how important would you say it is for them to kind of establish a baseline first? With the incident response plans and other things.
Absolutely. I think this is the time to start doing it. I think as cybersecurity professionals should be in there because what happens is they finish, just like we're talking about all those other emerging technologies, they finish building it. And then you show up and go, watch me hack this. And they don't want to bring you in anymore. So setting up those incident response plans, they're going to feel a lot more confident about the technologies that they're bringing to the groups, vendors, industry, wherever we're looking. So yes, simple answer.
I did have a second question.
Oh, okay.
So in a lot of areas in Mississippi where they have a lot of agriculture, obviously you have a rural problem where there's a lack of infrastructure to set up some of this infrastructure you need to kind of monitor some of this stuff. So do you have any ideas in mind of how to help expedite the establishment of this infrastructure? Because if you don't have infrastructure, you can't have the monitoring, you can't have the cybersecurity in place.
Yes. So I have been giving this a lot of thought. First and foremost, cybersecurity, if you look at it, also is a multi-billion-dollar industry. Very, very expensive in a lot of ways. And there are simple aspects that we can set up from a threat detection and monitoring that with the HughesNet network, I don't know if anybody's ever had HughesNet network out in their areas, there is still some simple low detection monitoring that can be set up from a IoT standpoint because we're bringing in both. I think there's an opportunity to simply slide in with the data collection, data monitoring. So yes, it is going to be a difficult challenge, and that's why I want to be here now to have this conversation as it gets brought forward.
David, you had a question?
I think I might have just gotten an answer to it. I was going to ask for people building products, building data products, is there something we should all definitely start to stick in?
So I'm going to get slightly technical real quick. The internet is a very much so duct tape and baling wire industry. If you didn't know, it actually was created by DARPA way back when, and then Xerox showed up and IBM showed up, and now we run off Ethernet, and then we ran into wireless, and now we have 5G, and now it's really confusing. The backbone of the internet is packets. So having something that captures simple internet traffic back and forth is very key. You're already actually doing it with the data collection. You're simply throwing out the headers that you're utilizing that are bringing in that data. It is very simple from a deterministic standpoint when you do data collection out in any of the areas to also underpin that to capture the network traffic in a net flow manner, which if you want to learn about net flow and IPFix, they're very fun and new ways to capture large data in very small, compact forms.
All right, we're going to have to stop now, but thank you very much. All right, I think we're down to our last speaker now. Can we get that loaded? Okay, so our last speaker is Jennifer Johnson, and she's going to talk about understanding how emerging ag technologies impact cybersecurity. So following on the same topic.
Great, thank you. So again, my name is Jen, and just to differentiate between Zeke and myself, because we did touch base saying we have very similar topics. While Zeke focused more on security, I'm focusing more on privacy. And a lot of people have no idea what that difference is. So let me tell you real quick, my dad built houses when I was growing up, so this is how I think about it. Security, it's your pipes, it's your plumbing, it's your walls. Are your walls square and plumb? Does the water run appropriately through your pipes? If you open and close a door, is there a sensor that says you open and close a door? Do certain people have the alarm code to get into the house versus some people do not? Those are your security tools and frameworks. Privacy is your interior designing. It's where you have put your TV. Who gets to hold the remote? Because we all know not everyone gets to hold the remote or change the channel. If you have a picture on the wall, that's your data. Who gets to choose that picture? Who gets to choose who comes in to see that picture? Who gets to choose and have authority to move that picture on the wall? That's the difference between privacy and security in a nutshell. I've discovered the importance of privacy in agriculture several years ago when I was at an identity conference. So everyone has a digital identity online. I happened to be walking next to this gentleman who looked very alone, and I struck up a conversation, and he was from John Deere, and I said, what on earth does John Deere have with identity information? And he blew my mind. John Deere has a ton of information about people's identities. They collect them from their equipment. You all know this by now. And so I fell in love with the topic of privacy and agriculture. I got somewhat distracted by healthcare and security, and so I spent a lot of time being a chief information security officer for healthcare companies. I'm returning back to agriculture. It's fascinating. I'm going to blow through some of this because I know I'm between you guys and lunch, and you already know a lot of this stuff. But types of data, there are several different types of data. Almost all of these are going to be collected by the technologies that we've seen presented here today and discussed academically. So public unclassified data, that's just anything you find in the old school telephone books or that's out there. Personal information, any data that can be reasonably inferred to identify who you are. So your name, date of birth, address, social security number, that kind of thing. Confidential data and proprietary data are more about what's exceptionally sensitive and may be captured as sensitive data in the agricultural industry. So your confidential data is going to be your really sensitive, might be financial data that your startups or your farmers have, whereas different proprietary data might be those trade secrets that those different farmers or ranchers are trying to capitalize on that they don't want other competitors to understand. Protected health data, that goes back to healthcare, protected health information. And consumer health data is like data that's on your Fitbit. That's not protected by HIPAA. The Ancestry&Me or 23andMe, Ancestry, that's all consumer health data, not protected by HIPAA. So it's important for everyone to understand that differentiation. Let's see. You know this slide, so I'm going to go past it. You pretty much know this slide too, so you have a lot of benefits to data collection. That's why we're doing all this advanced work. What I want to focus on is that there are also risks to this data collection using automated information and artificial information systems to capture that data, but then analyze, change, disclose, sell, use in different ways that you were not intending for that data to be used. There's a lot of different risks. And so it's worthwhile understanding what those risks are, and those risks are to the individual farmers, ranchers, forestry departments who are contributing that information. It's important for the companies that are providing the technology to understand what those risks are, as well as to understand what that implicates for the greater society. So you have data misuse, which again is someone collects your data and uses it for a purpose that you didn't agree to give. Financial loss and competitive disadvantage. If someone comes in and you get struck by ransomware and your product is suddenly, you've lost your funding, you get slapped with lawsuits, no one's going to trust you in the market again, you have huge financial loss. Sometimes breaches are they're game changers. They just shutter the whole building. That reputational harm, loss of trust, identity theft is still out there. It still happens. Business continuity, Zeke touched on. Productivity, if you have a business continuity issue and you're completely reliant on automated systems or drones that don't have backups, then you're down. Data provenance and ownership issues. So I love reading a privacy policy. I don't know about anyone else, but I've been going around and reading the privacy policies of a lot of companies that have been showcased by other speakers or that are out here. And it's interesting how they disclose data ownership of data that they collect and who has rights to that data, including if you're no longer using that product. Some of them say they may delete the information. And that doesn't mean that they will delete it. That may mean they keep it in perpetuity and do additional things with it, but you're not using that product anymore. So is that data your own still? So you need to be aware of those sorts of things. There can be reduced innovation, creativity to data collection. I actually tend to not agree with that one too much. This is what I really wanted to talk about. These best practices are also known as the Fair Information Practice Principles. In 1973-74, the Housing, Employment, Education, and Welfare Department of the United States recognized that, these things with computers and databases, and there's information. We should probably have some guiding principles on how to protect the data and provide guidelines for federal employees. So the FIPS was created. This is the foundational set of principles for every single privacy framework and set of guidelines in the world. You can take every single privacy framework, GDPR, PIPEDA, APEC, they all come back down to the FIPS. So privacy is largely industry agnostic, technology agnostic, and geography agnostic at the principle level. So it's always good for different industries to understand how these principles can be deployed. And so again, I wanted to walk through these. It's interesting, you can have security without privacy. You cannot have privacy without security. So that's a side note. I'm not going to go too far into security since Zeke just touched on it. I will say that there is a well-known triad called confidentiality, which means the data is secure, integrity, which means that the data is available, is correct, and in real time, up to date, and availability that the systems are up and running. But we'll walk through the rest. And so transparency, and I want to take a moment to also, how can people who are using these products maybe minimize the power imbalance. If you have a company that's coming in and saying, for example, with transparency, I read a privacy policy yesterday about one that was featured in a discussion, and they have their privacy policy for if you interact with their website, and they have it linked several times to the privacy policy of using their products, which is what I want to see. What are they claim ownership of and deletion, and what information are they passively or directly collecting? You can't get to it. So it's a dead link everywhere. They're not being transparent about your privacy rights with their products. And that's a power differential that's towards them, not the farmers. Individual participation, again, a lot of these websites talk about consent and that they will only use your data that they collect directly from you if you consent. But if you go into the fine print of those policies, they talk about a lot of data that they indirectly or passively collect, which you do not consent to, which is like your operating system, your geolocation, your, when you're interacting with the system, date, time logs, like then what are they doing to keep those secure? The authority, who gives them the authority to collect this information? With government, you usually understand it's a government directive, but you have to also understand what your consent is authorizing these organizations to do. Purpose specification and use limitation. This gets to my favorite use case that all product and tech guys like to throw out there. Some future use case. We're going to keep your data indefinitely for some future use case, which I, as a consumer or farmer or rancher, have no understanding about what that is and am not consenting to that. It just gives them all rights to your data to manipulate it, change it, sell it, if they keep it for some future use case. So you always want to make sure that in your contracts, the wording is very specific as much as you can get to it. Minimization, there's a principle that says you give the least amount of data that you need to do in order to perform the service or good that you're seeking that product to deliver. So if you're seeking information about plant health, it's really odd to me, for example, there's a crop platform, crop health platform I was looking at last night and this morning, and then I went to their privacy policies, and then I looked at the platform for their privacy policy, and it's all about crop health. That's it. But in their policy, they describe that they are collecting and storing and using your credit card information. Why do they need credit card information? So also nowhere does it say that company is PCI certified. So they have a lot of security holes in that. Quality integrity. What happens if you have an AI system analyze your data, it gets published or released, but it's wrong? How do you what's your redress rights to get your data updated? Access and amendment is very similar to quality integrity. Security we talked about, and accountability. What is the accountability for organizations to remediate or change if there are issues with privacy on behalf of the consumer, the farmer, the rancher, whoever is using these products, but then also the employees at these organizations. What's their accountability, and can they hold the organization accountable for their implement? So that is a really quick run through, and there's some information about me and my company. Happy to take questions.
Thank you very much. We have time for questions. Bruce?
Can anyone ever be assured that if you have data with a company, that if you want to delete it, that it actually is deleted?
Yeah.
And a recent example is 23andMe, and I've been hearing on the radio, oh, if you have data there, you should go in and delete it. But if 23andMe was doing things correctly, they've got multiple backups, and is data never, goes on forever, isn't that's my understanding?
Yes. First, I met the CPO of 23andMe 10 years ago. I was like, never contributing.
Yeah, me neither.
But so it's different. The United States, as much as we had the foundational principles, we are very behind on data protection and privacy regulations. Europe, South America, Africa, Asia, much more aggressive with financial penalties They have the right to deletion, and there is a very specific process that has to be followed, and they can have financial and criminal penalties levied. In the United States, you're starting to see some of that in different states. We don't have that overarching federal regulation. Interestingly enough, what most product companies in the United States try to do is say, if you want to have your account disabled, your information will not be available anymore. Not the same as deletion, but product and tech guys will try to use that language. With some of the emerging state privacy regulations, notably in California, there are very specific data deletion requirements and procedures that have to be followed that have those financial and criminal penalties, but it's not nationwide yet. That's a great question.
Okay, thank you.
Less of a question, more of a comment on your question. I used to be a data protection officer for a media company, and I can tell you my job as a BPO was not to protect your rights, but to maximize the value of our data assets and to keep us from to avoid fines and lawsuits. But I can tell you the development to truly delete data is really hard and takes a whole lot of work, because you have to, as you said, you've got backups and backups to your backups, and something's sitting on the developer's hard drive that he copied in to the development environment. Find all that, it's really hard. So you got to do, so anyway, my expectation is that when you ask somebody to delete something, if they're based in the United States, that's not going to happen.
So
unless it's HIPAA related. Once it's HIPAA related, then maybe.
Well, and also I'll get into that. So I learned privacy from a privacy engineering perspective. So I was not the typical lawyer into privacy. I was a practitioner who sat down with the back-end engineers and coders and programmers and UI UX guys and figured out how to codify privacy into the technology stack as well as policy stack. It is much easier to engineer privacy controls and processes in the beginning phase of building, because you have much less rework, cultural change that needs to happen, and lost files and databases.